All right, so today we're on properties of limits, and there are some things we can do with limits and things that don't work all the time. But we want to be able to evaluate limits using properties of limits, and also learn a numeric method for evaluating limits. So for evaluating limits, graphically, we're just looking for where the two sides of your function come together, like hopefully, and if they don't meet up close, if they don't get really close, then that limit does not exist. We can also use direct substitution, which we'll talk more about today. But one way that we can figure out a limit is maybe by estimating it numerically. And so this example is estimate the limit numerically by constructing a table. Maybe we want to draw a graph too. But here we have our function, and we want to know what happens when as x approaches 2. And we have this function right here, which when you look at that equation, what do you know? Because it's a rational fractional, what do you know right off the bat? It can't be 2. X cannot equal 2 right here from this denominator. We know that. And so right here in my little table of values here, I know right off the bat, if I plug in a 2, and I'll show it to you in just a minute, if I plug in a 2, what am I going to get as my, it's going to be undefined, okay? Just to fill out this table, these are my x values, and this is my function evaluated at x. And what we're going to do is we're going to try, we want to pick x values that are getting closer and closer to 2. And the nice way to do this, follow along on your calculator. So we're going to go to y equals. Yeah, I know. If you want to, why is it so...
second and the arrow. Sorry.
Okay.
Yeah, second.
There we go. Okay. Thank you. I'm going to go ahead and type in our little function here. I'm just going to use parentheses because I think the other way has too many steps. Over x minus 2. So I've got parentheses around my numerator and denominator. You could do the fraction thing if you want to. But what we can do is we have a table that we can use in blue, but I want to use very specific numbers, and I want to pick my own numbers. So there's table settings here in blue. So if you do second table settings, what I want is I want to be able to input my own independent variable. So go to the independent and highlight ask by hitting enter. And then it'll automatically give me the dependent variable. It'll give me the output, but I get to put in my own input here. So that's really, really nice. And then, I just want to go to the table. So go second table, and you can see we have this empty table. What I want to do is I'm trying to figure out what's the output as I get progressively closer to 2. So what's the value to the left of 2? Pretty close. 1.5, okay. And what would be really much closer than that?
1.6.
How about like 1.9? Oh, that's close. All right, and then what about?
1.99.
Okay, and I'm going to do 1.999. Okay, so I'm getting much closer to 2. And so let's see what happens when I plug in. I'm going to try 1.5, and I get 0.5, all right? And 1.9, and I get, 0.9. And then 1.999, and I get, 0.999. And I could go even further. I could do 1.9999999, and, and it gets me quite close to 1. Okay, all right. So it looks like I'm getting close to 1. So it looks like we're getting close to 1 question mark. If we were to get closer and closer and closer to 2, does that make sense to you? Okay, so now I want to choose numbers. And we can see when I plug in 2, what do we get? Error. So we knew that it was undefined at 2. So we knew that. Now I want to choose values closer to 2 from the right-hand side. So I could use like 2.5. And what's closer still? I'm sorry, is that right? Oh, okay, yeah. What's 2.1? 2.001. So, and again, I could, yeah, those get a lot closer. All right. So I'm going to try 2.5. That outputs a 1.5. I'm going to try 2.1. And that's 1.1. And then 2.001. Oh, 1.001. That's very, very, okay. And then, just for giggles, 2.0000001. And I get, oh, look at that. It's like 1. All right. So once again, as I approach from the right side, it does look like I'm getting very, very close to 1. Hi. I just got to grab something. All right. And so we're getting very, very close to 1. So what do you think that the limit is as we approach 2? So it is getting closer and closer and closer to 1. All right. And so this is how we can use the table to sort of get there. You'll notice if we actually do look at the graph, you can see that it is a line. Well, that's interesting. And you'll notice if you just do trace, and we were wanting to know what happened when x was 2, so you can see that at 2 it's undefined. But if I just click to the right, there's Tinkerbell, and it is getting close. Oh, it skips like right over 1 right there. So there just happens to be a hole in the graph. If you can imagine, this little graph just had a little hole right there when x was 2. But it is just a line with a little hole in it, which we can find the limit of. All right, let's look at letter B. So once again, we have x values and f of x values, and this is some crazy function right here. I'm not too sure what value x can't be. Hey, that's a thought we're going to talk about tomorrow, but yeah, should we factor it? Those, like this one, we could factor, right? Yeah, factor and simplify. All right. Yeah, so we'll talk about that more tomorrow. Let's go ahead and put this in. So x cubed minus 3x squared plus x plus 2 divided by x cubed minus 2x squared minus x plus 2. All right, I got mine put in. All right. And, do I want to look at the graph? I don't know. Maybe it's a good idea. Oh. Interesting. What's the limit? As x approaches 1, why doesn't it exist? Yeah, there's a vertical asymptote there. So that's okay. We know that that's what's going to happen. So at 1, it is undefined, just like before, because we have a vertical asymptote there. But again, we're going to see what happens numerically. So I want some values to the left of 1. What's very close to 1 on the left side? 0.5, or I'm just going to do 0.9, 0.99, and 0.999. I'm getting lots closer. All right. What's on the other side? 1.1, 1.01, and 1.001. Yeah, that's getting progressively closer. Whatever order you want to write those in, but all right. And so once again, I'm going to go back to my table, and I can delete all. Oh, I think I pressed clear and enter. Nope, it didn't work. I can delete all my values. And I'm just going to go ahead and plug in these guys now. Plugging in 0.9, I get 5.73, 0.99, oh, 50.75, 0.999, oh, 500. Look at what is happening, you guys. It's getting very, very large. Can we assume that it's going and getting higher and higher to positive infinity? Does that make sense? And I could even try, like I could do 0.9999, and it's like, ooh, 50,000, right? 50,000. crazy, okay? So it is growing very, very quickly. I moved 1/1000th and it jumped 500 spaces, all right? So huge. All right, on the other side, if I do 1.1, I'm at negative 4.23. At 1.01, I'm at negative 49. And then at 1.001, I'm at negative 499. All right, 0.2-ish, whatever. Where are these values getting closer to? Negative infinity. And so do they match? No, they're going in different directions. And so that is our limit does not exist. And we can see that we have an asymptote. All right, so depending on what our y values do kind of tells us if they're coming together to meet at the same point, then our graph is getting close to that same point. But here they're diverging, so we must have an asymptote. So we can use limits to kind of help us figure out what the graphs actually look like. Anyway, very good. I love the thought about factoring. We'll do that later. Oh, do I want to do this one? No, I don't really want to do this one. But I will, because it's a good one. All right, so last one here. Again, we have x and f of x. And I'm approaching 0. But I'm gonna try some fancy values here. First of all, we know what happens if I were to put in a 0 here. Undefined. It's undefined. X is not allowed to equal 0. We know that right off the bat. It would be undefined. But watch what happens when I look at some of these different values. If x is 2 over pi and 2 over 3 pi and 2 over 5 pi, 2 over 7 pi, 2 over 9 pi. Are you seeing the pattern? 2 over 11 pi. All right, let's see what happens.
What's the pattern?
I've got 2 over odd pies. Yeah? Okay. Sine of 1 over x.
Got that?
All right. So sine of 1 over x. Oh, I didn't mean to do that. I'm going to look at the table. And I just want to try and see what happens with these different pieces of pie here. Are these, like, this is weird, right? Because we're using decimals and we're getting closer and closer to 0. Do you know this is getting closer and closer to 0? Can you tell that looking at those? Okay, because what's happening? My numerator is staying the same, and what's happening to the denominator? It's growing, right? 3 pies is bigger than 1 pi, right? And 7 pies is bigger than 1 pi. All right, and so this is, we're cutting it into more and more pieces, so those pieces are getting smaller and smaller. So as we are getting closer and closer to 0, 2 over pi, we get 0.0274. Wait a minute, what? Oh, I'm in degree mode. I need to be in radian mode. Woof. Make sure you're in radian mode. Okay, so what was that? 2 over, pi? Oh, there it is. That's what I was looking for. It happens to be 1. Whoa, crazy, huh? And then this is why I chose these values. 2 over 3 pi. Oh, Jesus. I did that wrong. 2 over 3. Oh, I know why. 3 pi. I want to make sure that I'm dividing by the 3 and the pi. Careful when you put that in. Oh, tricky. What do you get? Negative 1. Oh, let's see. 2 over 5 pi. 1. Oh, and what's 2 over 7 pi? Negative 1. And what's 2 over 9 pi? 1. And what's 2 over 11 pi? Negative 1. And so, what is this one illustrating? Oscillating. This is an oscillating discontinuity. All right. So does the limit as we approach sine of 1 over x as we approach from 0, does it exist? No, it does not exist. This is an oscillating discontinuity. So it does not exist. The limit does not exist. That is not it. All right. All right. So, yeah, no, that is not it. All right, so properties of limits. Let B and C be real numbers. So C is like a 2, all right, or a 7, or a 0, all right? And B is also a regular number. This is a constant function, meaning it's like just a horizontal line. It's totally constant, like 3, y equals 3, all right? The limit as I approach any value on a constant function is just that value itself. There's nowhere to plug it in. There's no x to plug into, so it's just b. The limit as x approaches c, again, all we're doing is plugging in, substituting. Now, the reason we can substitute is because these are what we would call well-behaved. These are well-behaved functions, all right? This constant function is just a horizontal line. All right, we've got this line, which is y equals x, that's just a diagonal line. And what's x to some power? Like x squared. It's like a parabola, yeah? All right, and so it's a parabola or it's a cubic, all right? These are all just well-behaved, well, polynomials, really, all right? And because they're well-behaved polynomials, all we really have to do is we're just plugging in using direct substitution. So when we have well-behaved polynomials, we can just substitute. Substitute to find our limits. That's all we have to do. When they're well-behaved, nice-looking polynomials. Now, the other things we can do when we have limits is we can, maybe we have a function and it has a number in front. This number in front is called a scalar multiple. All right, all it's doing is multiplying. All right, and all it does is I get to pull it out in front, and I can just take the limit of my function f of x, and then I'm just going to multiply it by that scalar multiple. Recognizing a scalar multiple is going to be a very good skill because we're going to need it later. If I have two functions that we're adding or subtracting and I want the limit of them, well, I'm just going to take the limit of each function and then add those limits together. Okay, so that's pretty easy. Over here, we're multiplying two functions together. Guess what? All we get to do, find the limit of each and multiply them together. All right? And then when we have a quotient, I'm going to take the limit of the top and the limit of the bottom, provided that we're not dividing by 0. All right? The denominator is not allowed to be 0, ever. Okay? And if I have a function to a power, again, all I have to do is take the limit of the function, and then that answer I'm going to raise to whatever power it happens to be. Okay? These are basic rules. You'll see they work pretty easily. It's pretty straightforward. This looks confusing, but it's not really that bad. This stuff only works, and this is the important part, only works when the limits is defined. Okay, and this is really important. If we have a does not exist, can we do this? No, it's not going to work. Okay, so the limits have to work for it, these operations to work as well. So let's try a couple of these. Again, these are well-behaved functions. Consider the following basic limits for these well-behaved functions. What's the limit as x approaches 2 of 5? 5. What's happening here? This graph, this is my function, 1, 2, 3, 4, 5. This is the line, yeah, this is the line y equals 5. All right, well, as I approach on the x-axis, if I go to 2, what's happening with my y values? They're just at 5. They're always at 5, okay? What's the limit as x approaches 2 of x? 2. All we have to do is do direct substitution, just plugging it in. What is the limit as x approaches 2 of x squared? 4. It's 2 squared, which is just 4. Again, this is a well-behaved polynomial. All I have to do is plug it in to figure out my y value. Okay? Here, I'm adding two things together. So if I wanted to do this really, really mathematically, I would say, hey, I can do the limit as x approaches 2 of 5, and I'm going to add it to the limit as x approaches 2 of x. This is the limit notation. What is the limit of 5? This is 5. And what is the limit as x approaches 2 of x? 2. And when you add them together, you get 7. Okay? What is this 5 called? Scalar multiple. Thank you. It is a scalar multiple. And I can pull that out in front. And then I can worry about the limit as x approaches 2 of x squared. What is the limit as x approaches 2 of x squared? 4. We already did that. And so then it just gets multiplied by 5, and that is 20. All right, here I get to do the limit of the numerator over the limit of the denominator, provided neither is 0. Actually, 0 on top is fine. All right, what do we get in the numerator? 2. What do we get in the denominator? 4, which means gives me 1/2. So all of these are very, very well-behaved functions. There weren't any weird things since everything was a polynomial. All right, questions on those? All righty, last thing. All right, last thing, here we go. Evaluate the limits given the graphs. All right, so I have a product here, f times g. So I need to find the limit as x approaches 4 of f of x times the limit as x approaches 4 of g of x. Right? And again, this is the notation that you really, you should get used to writing, even though on Delta Math you're not really going to have to. All right, please pay attention to what graph you're looking at. Okay? I have f on top and g here down at the bottom. What's the limit as x approaches 4? -4, yeah. We've got a hole in the graph, but as we come from the right and move up from the left, we are approaching -4. And the limit as we approach 4 on the g graph. So as we approach 4, what happens on the g graph? Yeah, right here. Getting close to that point there, which is -7. All right, -7, and we multiply those together. What do we get? Positive 28. Okay. Here on this other one here, we've got a subtraction problem. So I want the limit as x approaches 6 of g minus the limit as x approaches 6 of our f function. And I'm just going to abbreviate that, which is fine. All right, so now which one do I need to look at first? G, the bottom graph here. As I approach 6, what value am I getting close to? 0. Minus. As we approach 6 on our f graph, we get close to here, which is -2. And 0 minus -2 is 2. All right. Woo. All right, on this one we have a power. I want to just worry about the limit as x approaches -2 of f. We're going to find that first, and then I get to square the result. All right, so I'm going to look at the f function. -2 is right here. What is our output? -5. Yes, we're getting close to -5. So that's negative 5, and we're going to square that, and what do we get? Positive 25. You'll notice I didn't use negative 4. Why not? So it's the difference between f at negative 2. Yeah, f at negative 2 is 4, but the limit are the y values nearby. Okay, not exactly at negative 2, but the y value is infinitely close to negative 2. All right, and then the last one here, I need the limit as x approaches 0 of f on top, and the limit as x approaches 0 on g on the bottom. Let's see, as x approaches 0 on the f function, what happens? Oh, it does not exist, right? Because we got to jump discontinuity there. And what happens when x approaches 0 on g? Same thing. We also have a discontinuity. We can't find either of those, so our limit does not exist. Okay? Do you have questions for me?